Okay, time is up. Okay, time for today's lecture. Again, thank you very much for showing up, and thank you very much for showing up on time. All right. Um. Okay. Every time I come to this class, somehow I get a feeling the atmosphere of our class or like our lectures is kind of um not so not so okay in upward direction. Let me put it this way. Okay. Now, so I really wanted to, well, I really hope you can have a more positive feeling about this class, about taking lectures in English. Okay. It is what it is. You are already enrolled in this program, which in the beginning, I think you already know that lectures supposed to be given in English. And we probably all have run into different kind of difficulties in doing so. But as I said it again, it will pay off. And I believe it is worthwhile, okay? It will make you more competitive in your future career, okay? All right, in the beginning of today's lecture, let's review signal spectrum. What is a signal spectrum? Anyway, the spectrum of a signal is the frequency content of the signal. All right. So when we talk about spectrum of a signal, what we are talking about are actually the compositions of the signal. Why do we not want to know the compositions of a signal? Because we want to know what it is made of. By understanding what it is made of, we can hopefully have a better understanding of how such a signal really is and what is special about it. And if we want to somehow adjust it, manipulate it, we know how to do that because we know its contents, we know its compositions. All right. How do we do that? Essentially, we find its Fourier series representation. In the beginning, we introduce trigonometry Fourier series representation, which, let me go back to that original representation, okay? This is a trigonometry Fourier series representation of the original signal x, whose independent variable is time, which is t. And in this particular case, we know that x is actually a periodical signal with t0 as its period. I'm sorry, okay, just say t0 as its period. So let me put 0 here. So with p0 as the signal period, omega 0 become the fundamental frequency of this Fourier series representation. And A0 is so-called the DC component, which is essentially the average value of the signal. And AN and BN are what we call Fourier coefficients. We don't like such a representation very much because every time for any given frequency, okay, we need to deal with two mathematical functions, okay? So why do we have to deal with two mathematical functions? If we can solve it, handle the same problem with one mathematical function. And that's why we introduce this compact Fourier series representation, which is the second type of Fourier series representation. Compared to the trigonometric Fourier series representation that we just mentioned, that essentially the same thing, okay? Because once you know A and B and which are the Fourier series, which are the Fourier coefficients of the trigonometric Fourier series, you can determine Cn and you can readily determine theta n by using these two formulas, okay? And this is what we call amplitude spectrum, and this is what we call phase spectrum. Now, let's go back to this representation. One of the reasons we like this representation because it is physically meaningful. Now, let's first look at this heading. Here, in the heading of this slide is that sine waves are the building blocks of all signals, okay? When we say sine wave, it doesn't have to be the sine signal. It can also be cosine because in a way, sinusoidal signal in English, if not particularly emphasized, sinusoidal signals refers to cosine, all right? Now, it is actually the building block of all signals, which means all signals can be synthesized by sinusoidal functions with different frequencies, okay? Now, we know that cosine is the building block, but for each of those building blocks, it actually have three parameters to determine the overall configuration or overall structure of that building block. The first element or the first parameters is amplitude, right? How big the size of the oscillation of this so-called sinusoidal function, amplitude, all right? The second parameter, phase, as demonstrated by this plot, phase actually determines the relative positions of these two sinusoidal functions in the time domain, all right? So it also has strong physical meanings. And finally, of course, frequency. It can be a low frequency cosine signal. It can be a high frequency cosine signal. It all depends on omega, all right? So essentially what we have is C cosine omega t plus theta, amplitude, phase, and frequency, three parameters. All right. Now, this representation, this heading is also very important. Any signal can be, well, let me put it this way. Any periodical signal can be decomposed into multiple sine waves with different amplitudes, phases, and frequencies, all right? So in this regard, you can see how fundamentally important sinusoidal functions are because this is what it can do, okay? By managing by choosing the right parameters for these sinusoidal blocks, you can do a lot of things. In particular, you can synthesize any periodical signals, all right? Now, let's introduce a compact Fourier series. Let me give you a compact series Fourier series example. Actually, I think we talked about this before. This is a non-periodical signal. Let me choose a region of interest, okay, in the time domain, which in this particular case is from t to pi, all right? So after choosing this period, I segment this portion of the response, the signal, okay? And I make it I make this segment of the signal repeat itself in the future and in the past. And after doing that, what I do what I have just done is convert this originally non-periodical signal to a periodical signal. All right, that's what I just did. And since this is known, okay, so I can easily use the formulas that I didn't review today, but we talked about it before. I can use formulas for Fourier coefficients to determine an and Bn, and later, I'm sorry, with an and Bn given, I can use the formula we just mentioned to determine Cn and Cn, which are the parameters of the compact Fourier series. Now, let me emphasize again, as you can see in this example, the size of Cn, that is the value of Cn, decreases monotonically with n, which means the amplitude spectrum decreases as the frequency increases. Okay, and this train is monotonic, okay, because it always go down and down, down and down. All right, and this is the phase spectrum. This is amplitude spectrum. The reason why we love these two plots is that visually, at a glance, by looking at these two plots, we can comprehend the frequency contents of this signal. Okay, so one picture is, in many cases, better than 1,000 words in terms of the information that it can convey. Now, same thing happened here. The good thing about these two plots is it helps us understand at a glance the frequency composition of the signal. All right. Now, we saw this before. This PowerPoint slide tells us when studying a signal, we can analyze the signal or visualize the signal from time domain, or we can study its frequency composition from the frequency domain. Okay. Let me ask you a question. If you don't answer that, it's totally okay. Okay. But if you have any suggestion, this student has been fall asleep from the beginning to the end. Should I wake him up to encourage his participation? Okay. Actually, okay. If you have any suggestion, because you probably know him better than I do, I talked to him. I suspect he has some sleep medicine problem. Okay. And I suggest him go to a doctor. I even recommend him a doctor. Okay. Because I had done such studies in sleep medicine. And so I have met some specialists, sleep medicine specialists as my research partner. All right. All right. Okay, so let's go back to control. Now, the physical meaning of amplitude spectrum is actually relatively easy to understand. The space spectrum, however, is another story. Now, what is the role of phase spectrum? Okay, why does it matter? What can it do for us? What informations can I get by looking at the phase spectrum? Phase spectrum is actually a function of how the phase changes with frequency. You all know that what phase is. Phase is actually determining the location of the sinusoidal function in the time domain. Okay, you can shift right to the right, you can shift to the left by changing the sign of the phase. Now, so if I recall correctly, at the end of last week's lecture, we talked about the role of phase spectrum. It has everything to do with shape information, which means that two signals can have identical amplitude spectra, but completely different waveform, okay? Their amplitude spectrum look exactly the same. But if you look at the waveform, that is how those signals vary with time, how the values of those signals changes with time. They could look entirely different, all right? Because they have different phase relationship. So the phase spectrum reveals how frequency components are aligned in time, okay? How they align with one another in time domain. Essentially, it tells you the timing relationship between different frequency components in the signal. So timing has everything to do with phase. Phase, timing, phase, timing, okay? Two key words. Thus, the phase spectrum is essentially for capturing the temporal coherence and fine structure of a signal, okay? So in this regard, a music, okay, does it make you feel easy, comfortable, okay, enjoyable, relaxing? It probably has more connection with the contents of the phase spectrum of that music, not necessarily the amplitude spectrum, okay? Because phase spectrum has a strong connection with the temporal coherence and fine structure of the signal, even though it doesn't directly relate to energy. Okay, who directly related to energy? Amplitude spectrum, all right? So, did I miss a remark here? Yes, okay. Let's go back to the compact Fourier series, okay? If I have a periodical function and then I develop its Fourier series representation, then each coefficient Cn corresponds a sinusoidal frequency at omega 0. Don't forget, omega 0 is 2 pi over T0, where T0 is the signal period. The energy contribution per period of power of the frequency component is this, okay? So if the signal has certain energy, then every of its component have certain energy, okay? And each component, the energy of each component is actually the magnitude, the square of the magnitude of Cn. Keep this in mind, okay? We will talk about energy more in the later part of this course. I think today, okay? Now, in addition to trigonometry Fourier series, compact Fourier series, we also introduce exponential Fourier series, okay? And we have shown that if I represent ft in this minor, then the Fourier coefficient Cn is actually defined as this, okay? Now, and if this is the case, then we know that Dn is actually a complex variable, all right? Now, let's look at this complex plane. Let's assuming that Dn is located here, okay? So this is its real part component, and this is its imaginary part components, okay? But when we view Dn, when we use Dn, we look at Dn from a polar coordinate perspective, all right? Why? Because the distance from origin to Dn is actually Cn over 2. That is 1/2 Cn, okay? Which is directly proportional to the amplitude spectrum. Similarly, from this triangle, okay, right triangle, we know that Cn is actually, this angle is actually theta, and which is the phase spectrum, all right? Which is the phase associated with the M0 and omega 0 frequency components, all right? So we can rewrite Dn as this, okay? This means we express Dn, which is a complex variable, okay, using its polar coordinates, where the magnitude is actually Cn over 2, or 1/2 Cn, and its angle is actually Cn, all right? Note that different from compact Fourier series and trigonometric Fourier series, when it comes to these dimensions, trigonometry and compact Fourier series starting from n equal to 0 and go all the way up to infinity. However, if I use exponential Fourier series to represent my periodical signal, then this n can be negative as well as positive, okay? So at the first glance, you would say, does that imply there is such thing which is called negative frequency? Okay, all right, because the value n, according to this representation, can be negative. And the simple answer is there is no such a thing called negative frequency. It simply does not exist in the real world, okay? Why does that exist in the real world? Because if you look at the definition of frequency, what does frequency means? If we represent frequency in hertz, okay, frequency means the number of periods per second, all right? For a frequency of 3 hertz, that means for every given second, the signal actually goes through 3 periods, okay? So if f is -1 hertz, what does that supposed to mean? Okay, in 1 second, the signal will go through 1 negative period. There is no such thing as 1 negative period. So this is the reason why negative frequency does not exist. The reason why we have minus n here, which at least, okay, seem to relate to negative frequency, is, all I can say is that it is a byproduct of the mathematical process, all right? Okay, so don't worry so much about negative frequency. But there are another thing that require our attention. That is, the magnitude of Dn is actually an even function, all right? Because the magnitude of Dn is exactly the same as the magnitude of D minus n. Similarly, the angle of Dn, which corresponds to the phase spectrum, is a function of frequency, okay? Because angle Dn is actually minus angle D minus n, all right? As demonstrated by these two equalities, all right? Now, how do we determine Dn? Okay, this is how what an exponential Fourier series look like, and Dn can be determined from this equality. Okay, we don't need it to prove it mathematically. Okay, but the structure, the configuration of this equality is actually very, very similar to the formulas of Fourier coefficients. Now, the point here is that determining Dn is important, okay? Because it represents the frequency content of the signal. And we need to deal with signals all the time. If every time we want to determine a frequency, the frequency spectrum of a signal, we need to do it by hands, then it's time consuming. It cannot be economically justified, okay? It cannot be sometimes financially justified, okay? So we need to come up with an algorithm to find a numerical algorithm to help us use a computer to determine the values of Dn by using a simple computer program. All right, okay? So the point, the task here is to calculate Dn using computer algorithms, okay? Now, what is an algorithm? An algorithm is actually a procedures that we can implement it using a computer to solve a given problem, okay? So behind the algorithm, of course, is a methodology. We'll find a method to solve the problem. And for this methodology to be able to convert it into an algorithm, we want to make sure there are two things we want to make sure. That is, there are only two things algorithm can do, okay? You can ask, that's the first thing algorithm can do is it can perform simple mathematical arithmetics, which involve subtraction, addition, subtraction, multiplication, and division. All right, and it should be able. The second thing an algorithm should be able to do that is that it can perform simple logic operations such as AND, OR, or XOR, and other logic operations. So the algorithms are made of those operations. So my methodology, once I have a methodology, I want to make sure my methodology can be implemented by using those operations. And by carefully putting those mathematical operations and logic operations together, I can compose an algorithm to solve my problem. Now, the algorithm now we want to study is numerical integration. Here, the goal is to find the numerical value, the result of this definite integral. It is called a definite integral because its upper and lower bounds are given, okay? So what is this definite integral really is? For the class of calculus, we know that if this is a function of, let's say, the horizontal axis corresponds to x, and the vertical axis in this figure represents the variable y, okay? Then this integral, the result of this integral, the value of this integral is actually the area under the curve of f, starting from x equal to a and ended at x equal to b, okay? So to find the solution of, or to find the value of this definite integral is actually the same as determining the size of the area under the curve of this this function. All right. So how do I determine this area under the curve? One simple and direct strategy is, the first thing is that I determine a sampling period, okay? And then by finding, by finding the values of f at these so-called sampling points, I can construct a finite number of rectangles, okay? Now, and by determining the area of these rectangles, one at a time, and finally, by summing these areas together, which represents the areas, the blue areas shown in this figure, I actually can determine approximate value of this definite integral. Of course, as you can see, there are errors. So this numerical errors is apparently inevitable, is bound to happen. But as you can imagine, if I make delta x smaller, then I can generate more and more rectangles, which are more densely distributed. And these arrows will go down, all right? And eventually it will die out. It will converge as delta x approaches 0, okay? So how to calculate dn using computer algorithm? Start with sampling. So what I need to do is first determine a sampling period. Okay, so t is the sampling period. Note that in signal processing, usually we need to deal with two periods. The first period is signal period, the period of a signal, okay? And the second period is sampling periods, okay? How often I need to sample a signal is determined by sampling period. How quick or how fast or how long the value of signal will repeat itself depends on signal period, all right? Now, let's now develop the algorithm, which is what we call TFT, or what is it supposed to mean? Okay, TFT, discrete Fourier transform, all right? All right, now, this is the formula that defines dn. Note that dn is the Fourier coefficients of the exponential Fourier series. Now, we have an integral here, actually a definite integral, all right? So, based on this idea, okay, let me construct n0 rectangulars, all right? So the number of sampling points is actually n0. If this is the case, then n0 is actually d0 divided by t. Remember that d0 is the signal period and t is the sampling period. Therefore, the number of sampling points within a period is n0, okay? So, and then I will go ahead to perform the sampling operations. So let me take the sampling values of f for each sampling points, starting from k equal to 0, go all the way up to n0 minus 1, because the reason why we need to stop at n0 minus 1 is that we only have n0 sampling points for one signal period, okay? So when go here from here, what we need to do is replace t by k capital T, all right? Note that k ranges from 0 to n0 minus 1. And similarly, this t has to be replaced by k capital T, 2, all right? Here. And this integral is replaced by this summation, all right? Now, this corresponds to the height, to the value of this integrand. So, in essence, this corresponds to the sampling values of the function of the integrand that we are dealing with. And remember, I need to determine the area of these rectangles. So if this is the height, this, of course, is the base of the rectangles. So their product become the area of the rectangle, and we have n0 of them. So we need to sum those areas together to approximate this integral, all right? This term stay the same. And we know that when t approach zeros, that is, if the sampling period is infinitely small, then this approximation will be perfect. Okay, there will be no numerical error whatsoever. Okay, so from this, the next thing I do is I rewrite this by noting that t divided by t0 is actually 1 over n0. And that's it, all right? And that's it, okay? Because with this representation, with this expression, I can actually write a program to determine this power series, okay? To determine the value of this series, because I know what f of kt is, and I certainly know this term, okay? So I can write a simple program to determine the value of this representation, okay? One thing I forgot to mention is that here I introduce a new variable, which is capital omega 0. And capital omega 0 is defined as the product of omega 0 times t. Now, one step at a time. What is omega 0? Fundamental frequency of the signal. What is t? T is the sampling period. So let me write it down. Omega 0 is actually 2 pi over t, 0, right? And if I time omega 0s by t, this is what I have. And then I can rewrite this expression as 2 pi divided by t0 over t. The reason I'm doing this is I want to introduce n0 into this representation. By noting n0, by noting that n0 is actually the ratio of t0 to t, okay? So this become n pi, 2 pi over n0. So I know that capital omega 0 is 2 pi over n0, okay? Now, omega capital, I'm sorry, capital omega 0 is what I call digital frequency. And omega 0 is what I call analog frequency. Okay? We will study their similarity and their difference in the later part of this course. But for the time being, remember the definition of omega 0. All right? Now, the next thing I want to do is I want to understand the value range of Dn, okay? Because from the original representation of the exponential Fourier series, Dn, the range of Dn actually go from n from minus infinity all the way up to n equal to positive infinity. By noting that Dn is actually an even function of n. So at least the range of n go from 0 to infinity. However, if I use numerical algorithm to determine the values of Dn, the value range of Dn is actually limited. Why is that the case? Let's first go back to this formula, which we used to help us to write a program to determine the numerical values of Dn, all right? Now, recall that we know that N0 is T0 over T. N0 is the number of sampling points per period. T0, again, is the signal period. T is the sampling period. And remember that we just derived this formula, okay? I'm sorry, this should be N0. We know that capital omega 0 is equal to 2 pi N0, right? Okay, so we have this result. Keep this in mind. So if this is the case, this is true, that is capital omega 0 is 2 pi over N0, then if I times both sides by N0, this is what I will get. All right? Now, when we go back to this representation, we know that for every given Dn, we need to deal with this term, okay, for every given frequency, okay? This actually is related to the nth harmonics of the signal, all right? So let's now replace n by n0, okay, and see what happened. If this is the case, I can rewrite this exponential function as this, okay? I just take them apart because I know ex plus e to x plus y is actually e to x times ey, all right? This is x, and this is y. I'm sorry, let me write it again, all right? And this term remains the same as this term. But here we know that N0 times capital omega 0 is actually 2 pi, all right? So this becomes this. And the value of this term is, of course, 1. Why is that the case? Because we know that because we know that E, according to Euler formulas, E to J theta is equal to cosine sine theta plus J sine theta, right? Okay, so in this case, theta is equal to 2 pi. Therefore, what we have here is cosine 2 pi plus j sine 2 pi. And we know that sine 2 pi is equal to 0, and cosine 2 pi is equal to 1. And this is what we get, all right? So what does it tell you? What does it tell you? If this is the case, then what it tells you is that the value of dn plus n0 is actually the same as dn, okay? Because the only difference between them is here and here, right? And if we go back to this representation, okay, to this result, or what we call numerical integration of the formula that defines dn. Let me rewrite it this way. If I want to determine is dn over n0, then everything stays the same. The only thing that is different is n becomes n plus capital N0, right? And this is essentially this, all right? So this is the reason why we come out with this conclusion. That is, by using this equality to determine dn, we are bound to have this result. And this result is not acceptable. It is not valid. It cannot be true, because it tells you that no matter what the signal is, its frequency spectrum will become a periodical sequence in the frequency domain, because its spectrum, okay, its Fourier coefficients, dn, their values will repeat themselves, okay, with a period of n0, okay? That cannot be true, okay? I'm not saying this will never happen, but you cannot expect every signal in the world to satisfy this formula, okay? So the value range of dn, therefore, is only good for this period, okay? That is from minus n02 to all the way up to n0 minus 2 plus 1, okay? Once you go outside this range, the value computed by DFT, the discrete Fourier transform, is no longer okay. It will give you the false answer. Now, remember, dn is not a real number. When you're using this equality to determine dn, what you will get is actually a complex number, which involves real part as well as imaginary part. But since we are looking at dn from a polar coordinate perspective, what we will get is actually the magnitude and the phase of dn. All right, let's take a 10 minutes break. 谢谢。麻烦看。